Okay, chapter 2, we're going to take a look at atomic structure and we're going to get into the periodic table. And by the end of this chapter, you should be able to find elements on the periodic table. You should be able to identify groups and periods. You should be able to describe charges, relative masses, and location of the three subatomic particles. That means the proton, neutron, and electron. So we're going to discuss that. You should be able to write an elemental symbol for a given set of subatomic particles. We'll get into that. You should know what isotope means and atomic weight. Write balanced equations for radioactive decay. We're also going to look at problems that involve half-life. So sometimes we call this the T1/2, the half-life. Describe the applications of radiation in health and medicine. Write correct electron configurations for each element through atomic number 56. So if you've ever studied chemistry at all, you've probably seen electron configurations. So if you remember the 1s2, 2s2, 2p6, etc., that's electron configuration. And if you've never seen it before in your life, don't worry about it. We're here to learn it. And then describe periodic trends in atomic radius. So you need to be able to discuss or describe trends in terms of atomic radii, first ionization energy, and what is known as electronegativity as well. So we're going to cover all these concepts in chapter 2. So let's start by digging into the periodic table. And how is the periodic table organized? Well, as scientists looked for order in their growing knowledge of chemistry, Mendeleev, who was a Russian scientist, created his periodic table with certain characteristics. And so Dmitry Mendeleev, when he published his first periodic table, or the first periodic table, out of the 118 elements that we know in the periodic table, he knew a little less than half, I think. So maybe, or maybe somewhere around 60 elements or something like that, right? He would have known things like oxygen, gold, silver, copper, right? He knew all those elements that people knew for a long time. And what he would do is he would make kind of like a card about each one, and he would write down, gold, and then he would write down the symbol AU, and he would write down the properties of that element, and then he'd make another one, for another element. Let's say he did one for carbon, okay, and anyhow, so then he'd write down what he knew about carbon, and what he would do is he would take those cards with all those different elements that he did know of back in the 1800s, and he would lay them down on the table, and he was trying to find some kind of pattern that he could organize the elements by, and that's where we get the word periodic from, right? Because if something happens periodically to you, it's repeating. And so there's a repetition, there's a pattern in the periodic table. And so when we look at the elements in the periodic table, first of all, we notice that they all have an elemental symbol, right? Like let's say I showed you for gold, it's AU, for carbon, it's C, for silver, it's AG, for tungsten, it's W, okay? For helium, it's He, for hydrogen, it's H, etc. And I would strongly encourage you to read the entire periodic table several times this semester to familiarize yourself with the elemental symbols. But you see the elemental symbols are either one or two letters that we use to designate each element, okay? And then furthermore, the periodic table is, not only do we have the elemental symbols, but the periodic table is divided, or I shouldn't say divided, I guess maybe divided into groups and periods, okay? So a picture is worth 1,000 words. So let's take a look at a periodic table, and I'll show you what groups are. They're the vertical columns of elements, and then the periods are going to be the horizontal rows of the elements. So let's go to the next slide, and you see a periodic table here. And if you look at the groups, okay, so this would be a group here. If I just put a quick circle around that, right? This would be group number 1, right? Then we go to group number 2, group number 3, group 4, group 5, right? These are vertical columns. Sometimes we call the groups families. I don't know if that term is used in the textbook or not. We'll just put here group. Okay, so this would be group 1, or sometimes it's called 1A, and I'll get into that in just a second. But the groups, again, sometimes we call them families, so maybe I'll write that over here, families. And if you think about people that are in the same family, they resemble each other, right, on account of genetics. And what happens is if you look at a group of elements, okay, like a family of elements, like fluorine, chlorine, bromine, and iodine. Those are what we call the halogens. It's a group that we call the halogens. Those elements, the fluorine, the chlorine, the bromine, and the iodine, they have a similar reactivity. Okay, so that would be one group. Another group that some of you may know of already would be this last group here. This is the noble gases, and as the name suggests, they're all gases and they behave similarly. So those are the groups. And then horizontally, we have the periods. So you can see here period. So we have period 1, 2, 3, 4, 5, 6, 7, like that. Now for the groups, you can see that we have the Roman numerals with the letters. So we have the A groups here, and then we have the B groups down here. I don't like to use the A and the B group system a whole lot. What I prefer to use is just 1, 2, 3, 4, 5, 6, all the way up to 18 for our group numbers. And this is accepted by IUPAC, which is the International Union of Pure and Applied Chemistry. Okay, so we've got our groups, we've got our periods, we've got our periodic table. We know there's some repetition in this periodic table. I told you you should practice going through all of the elements, and I'm not going to do it in this video, but you've got hydrogen, and then you come over here to helium, right? And then maybe I should zoom out. Then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, rubidium, strontium, ytterbium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon, so on and so forth. And so you should practice the names of these elements at least, and I would recommend that you practice the entire periodic table, but I don't want to spend too much time in our video doing that. Now the next thing you probably noticed is that that periodic table that we saw in the previous slide was divided into 3 colors, okay? We had the metals, okay? And if you take a look at the periodic table, you notice that by far, most of the elements in the periodic table are actually metals. They're the elements found on the left 2/3 of the periodic table. And common properties of metals are high thermal conductivity, right? Heat passes through metals very quickly. Electricity passes through metals, so electrical conductivity. High malleability. So malleability means it's bendable and it can be pounded into a sheet. Ductility means it's able to be drawn into a wire, and then luster is like a shine, okay? So if we go back to our periodic table here, you can see all the purple ones here. These are all metals. So again, the vast majority of the elements in the periodic table are metals. So after the metals, if we go back here, we have the nonmetals. So the nonmetals is the second largest group, and they're found on the right 1/3 of the periodic table. They're oftentimes gases or brittle, powdery solids, and they have properties that are generally the opposite of metals. And if you studied biology at all, you'll see that a lot of the elements that show up in your biology class, like carbon, nitrogen, oxygen, sulfur, phosphorus, right? These elements are all nonmetals, okay? You also see gases like helium, neon, argon, etc. But again, nonmetals are on the right 1/3 of the periodic table. And what does that leave us with? It leaves us with the the metalloids. Okay, so metalloids are here in beige. That's what we call like the metalloid line here. Okay, and you can actually see all the metalloids in here. So we've got boron, silicon, germanium, arsenic, antimony, tellurium, and this one down here is polonium. Okay, so those are the metalloids. And metalloids, it says here, metalloids are elements that form a narrow diagonal band in the periodic table between metals and nonmetals. And what's interesting about metalloids is that it says here they have properties somewhat between those of metals and nonmetals, and that's why they make you can make things like semiconductors out of them. So it says here metals such as yttrium in the color of the screen and lanthanum in the circuitry play important roles in your smartphone. You know, the way I think about metalloids is, you know, it's almost like the letter Y in that in some cases they act like metals, in other cases they act like non-metals. It's just like the letter Y. Sometimes it acts like a vowel, sometimes it acts like a consonant. Anyhow, so if we go back one more time, we have the metals on the left 2/3 of the periodic table. We have the non-metals on the right 1/3 of the periodic table, and then you get the metalloids just kind of tucked away in between the two. And there aren't many metalloids. There's what, 1, 2, 3, 4, 5, 6, 7 of them. So boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. All right, so let's move on. Another other subdivisions of the periodic table are the representative elements. And representative elements, sometimes you'll hear them called the main group. The main group elements. It means the exact same thing as representative elements. So sometimes I'll have students that'll look in another chemistry textbook, or maybe they will watch another YouTube video or something, and they'll say, hey, they called groups 1 and 2 and 13 to 18, they call them the main group elements. Well, it's the same thing as the representative elements, okay? Then we have the transition metals. So the transition metals is going to be groups 3 to 12. And at the bottom of the periodic table, everybody always notices the inner transition metals, which include the lanthanides, which are elements 57 to 71, and the actinides, which are elements 89 to 103. And so if we go back to our original periodic table, I'm just going to erase some of this stuff that I had written here. So the representative elements that were the main group elements would be groups 1 and 2, and then it would be groups 13 to 18, okay? So that would be representative elements, okay? Then down here, okay, from 3 to 12, this would be transition metals. And then down here, these are what we call the inner transition metals, okay? We also call them, I guess you could just call them the inner transition metals. But some people like to call them the lanthanides and the actinides because they start with lanthanum, element number 57, and actinium, element number 89. Okay, so there are a few specific families, and remember I told you groups is the same thing as families. Okay, they mean the exact same thing. Groups, families, synonymous. So there are some specific families or groups in the periodic table that you need to know, okay? I'll tell you exactly which ones you need to have memorized. The ones that you need to have memorized, I'll put a red check mark, are the alkali metals, which is group 1, except for hydrogen. If you're like, why not hydrogen? Well, hydrogen isn't a metal, it's a gas, okay? So hydrogen could actually be placed over here in the periodic table. And sometimes you'll see people do that. They'll scribble it into the periodic table in a classroom maybe. But we're not going to do that. We're just going to leave it there. And if you're like, well, why is a gas on top of a bunch of metals? That will become abundantly clear later on. But anyhow, group 1 is the alkali metals. You also need to have memorized group 2. Okay, so we've got group 1, alkali metals. Then group 2, which is the alkaline earths. Notice the difference, right? You have alkali, alkaline. Okay, so alkali metals and the alkaline earth metals. Then the other two groups that you need to have memorized are going to be the halogens and the noble gases. So you can see the halogens, it's going to be group 17, and noble gases is going to be group 18. Trust me, Mr. Dion knows about the other groups, like the coinage metals, the chalcogens, the pnictogens, okay? But the only ones that you need to know for this class, again, are going to be, what did I say? Alkali metals, alkaline earth metals, groups 1 and 2, respectively. Halogens, group 17, and group 18 is the noble gases. Furthermore, with the halogens, really the only halogens that we're going to be discussing in detail, so halogens, would be fluorine, chlorine, bromine, and iodine, okay? There you go. So you can see there's, maybe a little bit more division in this periodic table. But there you go. That's everything you need to know. And you can see that they gave you even more information here. They said the element symbol indicates the state at 0 degrees Celsius and 1 atmosphere. So we can see here sodium has an atomic number of 11. We'll get into that later on. It has a symbol of Na. That comes from natrium, which I think is Greek, maybe. Anyhow, then you have the name sodium, and then you have the standard atomic weight. And we're going to get into that a little bit later on. But before we do that, let's try solving a problem that just involves identifying some elements in our periodic table. So use the periodic table in figure 2.4 to classify the following elements into their specific family. So I'm just going to write down group number, okay, for each one of these. So neon is in group 18. So if I zoom in here, maybe I'll use my blue pen. There's neon, which is in group 18. So it is a noble gas. So we'll scribble that down here. So we'll put here A is a noble gas. B, cesium, is in group 1. So here we'll put group number 18. Here we'll put number 1. So if it's in group number 1, it's an alkali metal. So we'll put here alkali metal, not alkaline earths. That's group number 2. Gold. Where's gold? Okay, so let's find gold. Gold is down here. It's element number 79, and it is one of the transition metals. It's in group number 11. So we'll scribble that in here, number 11. And so gold is a transition metal. Then we've got germanium. So let's find germanium. Okay. And you see that germanium is right here. And so germanium is a metalloid. So it's in group number 14. So we'll just put here number 14. So germanium is a metalloid. All right, there we go. So we were able to identify maybe not the specific family for group 14. It doesn't have a specific name. Okay, we'll just say number 14, but it'd be classified as a metalloid. All right, let's talk about subatomic particles. And you might remember that I told you about the Greeks, right? The Greek philosopher Democritus, he came up with the idea of atomos, okay, which he said was the smallest particle that could exist. And the thing that the Greeks lacked was experimentation, right? They theorized about all these different ideas, but they didn't do any experiments to prove or disprove these ideas. It wasn't until the 17 and 1800s, once scientists like Lavoisier started doing experiments and John Dalton, that the atom was really discovered. And we now know that an atom is actually made out of other particles that are smaller than an atom, namely the proton, the neutron, and the electron. All right, so the ongoing quest to discover the true nature of the atom is one of the greatest examples of the scientific method in action. It took a lot of people, a lot of time to discover the atom, to understand the nucleus, to figure out what a proton was, an electron, and a neutron. And we're not going to go through all the history of that, but one of the landmark discoveries was the identification of the 3 subatomic particles that make up atoms. So let's take a look at them. They are the electron, okay? The symbol that we use for an electron is just E with a negative sign like this as a superscript. Then a proton, I usually just use the letter P, but you could put P with a positive superscript or H with a positive superscript. If you're like, well, why would that be? I'll explain that later on. Then we have the neutron, which I just like to represent as the letter N. Now, when it comes to charges, you see the charge of an electron is -1 and a proton is +1. And a neutron, like the name kind of suggests, neutral. Okay, a neutron is 0, has no charge. Now, on top of that, you'll notice probably very quickly that the location of the proton and the neutron is inside of the nucleus, whereas the electron resides outside of the nucleus. And I'm sure a lot of you knew that before ever taking a class like this. You know, you might see a picture somewhere, you know, where you see something, you know, that looks like this as a nucleus. Then you see these kind of electrons going around in orbits like this, which isn't scientifically accurate, but the idea is there that protons and neutrons are in the nucleus or in the center of the atom, and electrons are on the outside. And we're going to get into that a little bit more. But what I really want to park it on here for a second that I think you might find kind of interesting is check out the masses of these things, okay? So look at the masses of the electron, the proton, and neutron. So check this out. The proton and the neutron are found inside the nucleus, okay? And you can see they both have approximately the same mass. Now, I say approximately, even though it looks like they're identical here, because it doesn't show you all the mass sig figs. But anyhow, 1.67 times 10 to the negative 24 grams. So they're very small, but you notice again that the proton and the neutron have approximately the same mass. But check this out. Look at the electron. The electron has a mass of 9.07 times 10 to the negative 28. That means it's about 2,000 times lighter, smaller than a proton or a neutron. So we can put here for our electron, it's approximately 2,000 times smaller, or maybe I could say lighter, but we'll just say lighter than proton or neutron. So if you think about the mass of an atom, by far the vast majority of the mass comes from where? It comes from the protons and the neutrons. Very little mass comes from an electron, so much so that if you lose an electron from an atom, it doesn't affect the mass whatsoever. It's like if you went on a scale at the doctor's office and they checked your weight and they said, okay, well, you have a weight of 120 pounds. And then you said, oh, hold on, there's a piece of lint on my sweater. Let me pick that off. And then they reweighed you. Well, that's pointless, okay? So an electron is much, much smaller than a proton or a neutron, about 2,000 times lighter. So this slide just kind of rehashes what I just went over, but we'll cover it. Again, a proton has a charge of +1. It's found in the center of an atom. It has a mass of 1.67 times 10 to the negative 24. A neutron is found in the center of an atom, has no charge, okay, 0 charge, has the same mass as a proton, pretty close. A neutron is actually a tiny bit heavier than a proton. And then we have the electron, and electrons are found outside of the atom. So it says orbits the center of the atom, has a charge of -1, electric charge of -1, and a mass of 9.07 times 10 to the negative 28 grams. All right, so there we go, proton, neutron, and electron. Now I told you that we weren't going to be covering every last morsel of the history of, the discovery of the atom, who discovered the proton, neutron, and electron, but we're going to cover a little bit here. And we're going to start it with an English school teacher by the name of John Dalton. And he published something called Dalton's Atomic Theory back in the 1800s. And I believe that there's 6 points to his theory. And today, in 2025 and beyond, it says here 2023, but anyhow, in 2025 and beyond, out of 6 postulates that he made in his atomic theory, 4 of them are still correct today. So you think that's pretty remarkable. Anyhow, so first of all, Dalton proposed that atoms were themselves little particles, tiny particles of matter that could not be created or destroyed in a reaction. He postulated that atoms of each element are similar to, yet different from, atoms of other elements. So he said if you have an iron element, it's going to be made of the same components, protons, neutrons, and electrons, then a silver atom will be made of protons, neutrons, and electrons, but it's going to have differing number of protons, neutrons, and electrons. And then I like this last one. Molecules are formed when 2 or more elements combine. So molecules, and you think about it, molecules are always formed with whole number ratios of atoms, right? Think CO2, right? 1 carbon, 2 oxygens. Think glucose, C6H12O6, right? There's no such thing as C1.2O5.8, right? That doesn't exist. They always combine in whole numbers, all right? So Dalton's theory needed to be updated once charged subatomic particles were discovered. So Dalton didn't know about the proton and the neutron and electron, but his postulates about atoms and how they form molecules are largely still true today. Now, J.J. Thomson, he is the father of what we call the plum pudding model. Okay, and you can see they put a picture of plum pudding here. So the way Thomson thought of the atom, there's not a lot of room to sketch here, but he thought the atom was kind of like this, that you had all these electrons, okay, which have negative charges. Maybe I could have put a circle around each one of them. And he said the electrons are just kind of spread out around the atom, and then there's just positive all throughout. So he said the electrons are like the raisins inside a plum pudding, okay? And Thomson was revered. I mean, he really was. He was very highly respected. Don't think this guy wasn't respected. He really was. I mean, he won a Nobel Prize. And so the pudding would have to consist of some kind of positively charged matrix, right? So when I wrote that positive charge here, positively charged matrix, that's what I'm just writing here. It'd just be like a positive body, and that positive body or matrix would balance out the raisins, the negatively charged electrons, okay? And again, Thomson was highly revered, won a Nobel Prize, very, did some amazing stuff. He discovered the electron. I mean, so that's pretty cool. But in science, there's always a rebel, right? There's always some like the bad boy of science, or the bad boy of the time. And I guess, I don't know if he's a bad boy, but anyhow, kind of the rebel of the day was Ernest Rutherford, okay? So Rutherford was from New Zealand, I think. Anyhow, and again, I'm not going to say that everybody believed Thomson's model, but I'd say pretty much everybody believed it. Okay, again, I'm telling you for the third time, he won a Nobel Prize. But Rutherford didn't believe it. He said, I don't think that Thomson's model is correct. And he did one of the most famous experiments in all of science called the gold foil experiment, where he shot positively charged particles that we call alpha particles, which is really just the nucleus of a helium atom, but that's neither here nor there. And he shot these charged particles at a piece of foil, okay? So here's the idea. According to Thomson, if you fired your alpha particles, so alpha particles, that's what these black lines represent. According to Thomson's model, if you fire alpha particles at this piece of gold foil, okay, the alpha particles should just go right through. But what Rutherford said was he didn't believe Thomson, and he thought that there was a positively charged body that was very dense in the center of the atom, which you probably know, especially if you read the chapter, you'd know this is the nucleus. Now, we know it's true nowadays, but they didn't know at the time. And so Rutherford kept firing alpha particles at this gold foil. Okay, he'd fire them and fire them and fire them. And most of them went straight through. Okay, and so the gold foil is shown here. This is just showing one atom of the gold foil. Okay, and so what happened is most of the alpha particles just went straight through, but then they kept firing them for days and days and days. And then all of a sudden, they saw something really cool. One of them started to be deflected, like ricocheted off. Another one ricocheted off. And then eventually they saw one coming back at them, okay, or back towards them. And when he first published this, he wrote this whole idea of the alpha particle coming back towards them. He said, this is the same thing as taking like a 10-inch shell from a cannon, firing it at a piece of tissue paper, and then it bouncing back and coming back at you, okay? So just totally crazy, blew the lid off the whole thing, and he discovered the nucleus this way through the gold foil experiment. And so he proved that the nucleus was a central core that's found inside an atom, and it contains protons and neutrons. And in fact, most of the mass of an atom is in that positively charged nucleus, which again is found in the center of the atom. So Thomson's model out, the Rutherford model in.